So it's a great pleasure to introduce our speaker of tonight, Stephen Wolfram. It's one of those persons that actually doesn't need an introduction, but I cannot resist to give a short introduction. So Stephen Wolfram is the founder and CEO of Wolfram Research, the creator of Mathematica, Wolfram Alpha, and the Wolfram Language. He's also the author of A New Kind of Science and other books, and the originator of the Wolfram Physics Project. And so I'm happy to give the floor to Stephen Wolfram and present his lecture from West Coast, US, in North Coast, the Netherlands.
Hello there. Well, nice to be with you this evening for you. Sorry I can't be there in person. But what I wanted to do was to talk a bit about computation and its significance for everything. I mean, I think computation is kind of, as an idea, kind of the most important thing that has emerged in the past century and that will probably dominate what comes in much of the future. And I think what I wanted to do was to kind of, I've been involved with thinking about computation and trying to kind of understand what the implications of computation are for about 45 years now. And I'm rather happy to say that in several directions, we've managed to get a long way. And I thought I would try and summarize a few of those things here. And hopefully I won't yak on for too long and we'll have a chance to have some discussion and questions after that. So first question is kind of to talk about computation, raw computation in the wild. What is it like when you just do computation and nothing but, so to speak? And so one of the things that I got interested a long time ago in is if you're just looking in the computational universe of possible programs, what's out there, what happens out there? And so the particular kind of programs that I was found most useful to study are these things called cellular automata. And here's a typical example of the program, the rules for a cellular automaton. You just got a line of cells, each either black or white, and at each step, you just update the color of a particular cell by looking at its neighbors and applying this particular rule. So you might say, very simple rule, should do only very simple things. Let's actually see what it does. Let's just run this particular rule. Let's say we started off from a single cell initial condition. We run it for like 40 steps or something. Let's just show it like this. We'll see what it does. Starting with this very simple rule, applying it at every step to every cell, here's the pattern we get. Okay, let's change that rule a little bit. Let's change it to this rule here. Now let's run this again, see what we get. We'll get a slightly more elaborate pattern. If we were to continue that a while longer, we would see that from that very simple rule, we'll get this very intricate pattern, although it's still in a sense, a very regular, in this case, nested fractal kind of pattern. So an experiment I did a very long time ago now in the early to mid 1980s, was just to say, if we sort of point our computational telescope out into this computational universe of possible programs, what's out there? So let's just take a look at, for example, all possible programs of this general kind. There are 256 of those. And let's just say let's do this. Let's just, and I'm just doing this as a live experiment in Wolfram Language here, just so can see what's involved in kind of the computational, exploring the computational universe and kind of with a computational telescope. So this is what we get, just looking at all possible rules of this kind. So we see a lot of them behave in very simple ways. You start off with this one black cell, just moves across the page and so on. Sometimes you'll get these nested patterns here. My personal all-time favorite science discovery is what happens when you get to rule 30 here. And so let's just run that a little bit longer. Let's look at what rule 30 is. It's just has this form here, and let's just run this for a bunch of steps. Here's what it does. So this is a very surprising thing because we have a very simple rule here. We're starting it off from just one very simple cell as its initial condition, yet the result is that we get this very elaborate pattern of behavior. And this is something, and for example, if we look at the center column of rule 30, then for all practical purposes, it seems to be completely random. We used it as a pseudo-random generator for a long time. I actually have some prizes out there for being able to prove almost anything about that center column of Rule 30. But so the thing that we learn here is out in the computational universe, even very simple programs can produce very complicated behavior. It's something that kind of goes against our ordinary intuition, because our ordinary intuition tends to say, if we want to make something complicated, we have to go to lots of effort to actually, we have to have some complicated plans, complicated processes to make something complicated. But that's not true in the computational universe. In the computational universe, it's sort of effortlessly possible, even for very simple programs, to produce very complicated behavior. What I was at first interested in long ago about that discovery is that it kind of tells one something about nature. Nature has this feature that it seems to very effortlessly make all kinds of very complicated things. And I think this is kind of the secret that it's using, that out in the computational universe, it's very easy to get very complicated kinds of things. Our traditional approaches to, for example, mathematical science didn't tend to see this, because typically what we have set up are cases where we can set things up so that we readily can foresee what will happen. When we just look, sort of point our telescope out into the wilds of the computational universe, we always are finding these things where even though the rule is simple, the behavior is not. So we can ask questions about this. Like, for example, one good question would be, what's this going to do after 1 billion steps? So often in sort of traditional mathematical science, the thing one is most proud of is being able to say, I've got this, this representation, these equations for some system. I can work out what the system will do after a huge amount of time just by filling a parameter into these equations and reading off the answer. But the question is that kind of notion of prediction, is that, oh, the system is going to take a lot of effort to go figure out what it will do, but we, using our mathematical equations, can kind of jump ahead and see what the answer is. Is that something that is a general thing that's possible or not? One of the things that we realize from this is it's not possible in general. You can clearly find out what this is going to do after 1 billion steps by just running it for 1 billion steps and seeing what happens. The question is there a way to reduce that computational effort and work out the answer, predict the answer with less computational effort? Well, we have pretty good evidence. We know in some other cases, we don't yet know specifically for this Rule 30 system, but we have pretty good evidence that this system exhibits what I call computational irreducibility. That is, that to find out what it's going to do, there's basically no better way to do that than to just follow each step of what it explicitly does to do the same sort of irreducible amount of computation that it does. And that's an important thing if you're thinking about science, because one has been led to think that perhaps science would let one predict everything. But yes, this is saying from within the kind of insides of science, it's saying there's this phenomenon of computational irreducibility, which limits what can be predicted on the basis of even knowing the rules by which a system operates. And in a sense, that might seem like a very sort of negative conclusion, that there's this limit to science, which there is, but it also has a lot of positive consequences as well. So for example, if you ask a question as we lead our lives and time progresses and so on, what has been achieved by the progress of time? And you might say, well, if we could just jump ahead and say, don't live out those years of life, just use the formula to tell you what the answer is going to be, and it's 42, for example, then that's kind of that means that nothing is really achieved by the passage of time. What computational irreducibility means is that there is something, in a sense, really achieved by the passage of time. It's this sort of irreducible computational process that corresponds to the things that happen as a result of the passage of time. And by the way, this phenomenon of computational irreducibility is also, in the end, what's responsible for things like the second law of thermodynamics. The second law of thermodynamics kind of tells one that you can start with something like molecules of a gas in a box or something that are arranged in a very simple, orderly way, and they will tend to get more and more disordered over time. The reason that ultimately happens is because the process of collisions between molecules and so on is a computationally irreducible process that's leading to this kind of irreducible amount of this sort of this computational irreducibility, which we can't decode, when we look at the molecules in the gas after they've evolved for a while, they look random to us for the same reason that the center column of Rule 30 looks random to us. So in any case, you can kind of go out into the computational universe and sort of look at raw computation. I don't know, let's pick an example. Let's just make some raw. I've just made something with 5 colors instead of 2 there. Let's go ahead here. Let's just make a whole bunch of these. Let's just do a little bit of parallel computation. Let's make 100 of these in parallel. Let's see what happens here. Okay, there we go. So each one of these, in a sense, is a representation of some kind of artificial universe out there, and this is showing what it does. And you'll see that all kinds of different elaborate things will happen. I don't know, we could pick any of these. This is kind of raw computation. This is what it looks like. And out in the computational universe, there is sort of an infinite amount of this kind of raw computation. So I want to talk about 2 things. I want to talk about how we connect raw computation to what we humans care about doing. And I want to talk about how this idea of raw computation in the end ends up being the way that our whole universe actually works underneath. So let's talk about sort of connecting this to human purposes. The thing that I've spent a lot of my life working on is building the computational language, Wolfram Language, which is an attempt to kind of represent computationally the things that we humans care about. This is kind of looking out in the computational universe of all possible computations, but there are particular things that we humans care about. Like we might say, I don't know, let's get a list of words in English or something, and we could say, let's work out what's the that's something we care about, words in English, for example. Let's say we take the first letter of words in English, and let's make a word cloud of what the most common first letter is in English. I don't know. I'm curious whether I could do this for Dutch as well. Let's try. There we go. Okay, so no doubt people in the audience will know what the answer is. What's the thickest section in a Dutch dictionary by number of words that start with that letter? Or we could, for example, we could say, let's just take I think you're in a planetarium, so let's ask about planets, for example, and let's say we make a list of planets, and for example, I don't know, we could just get this is all the sort of the whole point of our computational language is to have computations that relate to things that are actually relevant to our world. They're computations that sort of we humans care about. So for example, here are some images of planets. Let's pick up one of those images, for example, here, and let's say we could do some computation on that image. Do this. We could take, I don't know, we could take these particular images. Actually, I'm really curious to do this. Let's just make a feature space plot using machine learning. Let's make a feature space plot of those planets, which are on line 16 there. And let's see how machine learning kind of clusters these not very many planets into groups. I don't know what we're going to see here. Probably go to, oh, there we go. Okay, so we have, I see. Not too exciting, but we can get some sort of sense of how the visual appearance of these planets is clustered around. Or for example, let's say we deal with our kind of practical world. I think you guys are in Groningen. Let's see if we know about that. Let's see if we know what the population of that city is. Okay, and maybe we can find out what the population has been like over the course of years. Let's see whether we can get a time series of, okay, not very many data points, but we can at least plot that. This is kind of like knowing about the world computationally. For example, we could go ahead and we could say, let's do the following. Let's say we make a geodisk centered on Groningen, and let's make it the radius of the geodisk be, let's say, let's do the following. Let's say it's 1 kilometer, 10 kilometers, etc. So let's say quantity, we say 10 to the n kilometers, and we might say, and then let's say we make a table of geographics of that, with n going from, let's say, 0 to 4. Okay, so what this should do, if I got this right, let's see, did I get it right? Is make, oops, I didn't get it right. Oh yeah, go. Is make a picture that shows kind of a map of the Earth centered on Groningen, successively powers of 10 going out from that place. And I'm sure we can, let's see the result of that. And I don't know why this is running more slowly than I would expect. It's okay. It's probably loading in all sorts of data on the detailed streets of Groningen here. In any case, all right, there we go. Finally, okay. So that's probably it's probably based on where it thinks the center of Groningen is, and no doubt we could go and pick up that picture, and we could make a satellite image, get a satellite image of that, and start doing image processing on that, and so on. I mean, I could take that image there, and I could just say, do something like edge detect in that particular image, and get a result from that, and so on. So, okay, so what's the bigger picture here? What we're trying to do is to take those parts of the computational universe that we humans at the current time in history care about, and have a representation of those things that is as convenient for us humans as possible. We're trying to make kind of a language so that you can think about things, so you have kind of a notation for thinking about things computationally. And kind of the history of that kind of effort, if you go back 400 years, you'll get to a time before mathematical notation, before plus signs and equal signs and so on were invented. And then when people wanted to talk about things mathematically, they had to just use words to do it. After the invention of mathematical notation, things were able to take off very nicely. Algebra was invented, calculus, all the mathematical sciences were developed because there was this kind of streamlined way to talk about and think about mathematical kinds of concepts. And our goal with Wolfram Language is to provide the same kind of thing, but for the much broader collection of capabilities that are involved in computation. And so that's something where we can represent a lot of kinds of things in the world computationally. And the goal is so that we provide a language, so once you can formulate your thoughts in that language, you're formulating your thoughts about something computationally, and then it's up to us to implement the language so that you can actually do computations based on that. And kind of the goal here is to sort of enable computational X, enable, just like all the mathematical sciences were enabled, to enable all of the computational sciences, and to provide a way for sort of humans to have a notation in which to talk about things computationally. So that's kind of one direction, is going from the sort of what's out there in the raw computational universe to the things that we humans currently care about. I want to talk about a second direction, which is kind of going down to the way that the universe actually works underneath. And so one of the things one can ask, once one's seen, Rule 30 and all these kinds of things, very simple programs, very complicated behavior, one could ask, well, what about the most extreme version of something like that we can imagine, which is our whole physical universe? Could it be the case that our whole physical universe is based on some very simple, let's say, computational rule, and that the universe is sort of grown from that rule, and that everything we experience is part of that story? Well, I had thought about this for a long time. In the 1990s, I had figured out a certain amount about this, and I got a certain distance by the beginning of the 2000s, and then kind of stopped and worked on many other kinds of things about computational language and so on. And then about 3 years ago, restarted as a result of both a particular technical idea I had and some young physicists being very enthusiastic about seeing this make progress. I restarted thinking about, could one take these ideas about computation and apply them to understand how our physical universe works? And the huge surprise is that it worked unbelievably much better than I could possibly have imagined. And I think we can now say with pretty great confidence that we kind of know at least the framework for kind of the machine code on which our universe operates. And what's been really nice is that many approaches in mathematical physics that have been taken in the last several decades managed to plug into the kinds of things that we figured out. We've provided kind of the lowest level machine code for what's going on, but all sorts of limits of what we've done, all sorts of particular cases of what we've done turn out to be things that have shown up in the mathematical physics of the last few decades. These things all now have a way to get a common foundation, which is pretty nice and pretty encouraging in terms of what we're doing. Okay, so the question we can then ask is, with that idea of sort of I think your conference is called the InformationUniverse. Let's talk about what the actual universe is like. I talked about the computational universe of possible programs. Let's talk about our particularly physical universe and how it relates to that. And in the end, we'll see some very, very general kinds of things that come out. But let's start off with just talking about kind of the how to think about our universe. And there's a great deal of detail here, which I'm certainly not going to go over all of, and there's thousands of pages that have been written about this already, and lots of people who working on it, and so on. So it's kind of a big enterprise, and I will just kind of give you the very basic outline. So, question is, what's our universe made of? And one of the key ideas here is to go away from something which has sort of been almost an assumption for the last few thousand years about what is space. And from Euclid on, people have had kind of the idea that space is just something where you put things at a certain position in space. You don't ask, what is space made of itself? You could say the same thing about some fluid like water. You could say water just flows, you can put things in it, et cetera, et cetera, et cetera. But we know that at the bottom level, water is made of something. It's made of a bunch of molecules bouncing around. So the first sort of big statement about what we're doing here is to imagine that space is actually made of something. It's made of a bunch of discrete points, a bunch of atoms of space, and in a sense, all we know about those atoms of space is how they're connected to each other. We don't know where they're placed because there is no notion of space. It's just a bunch of discrete points, and each point is related to other points. We can think of it as forming some kind of graph or hypergraph, where we're just saying each point is connected to certain other points. So the other thing that's sort of extreme here is that we imagine that the only thing that exists in our universe is space, and that everything that we experience, all the particles and all these kinds of things, the electrons and quarks and photons and so on, they're all made up from pieces of space. Now, in a sense, that's something there are things like, for example, imagine you've got some water and you've got a little vortex that's formed in the water. The vortex is just made of a bunch of molecules underneath. It's just made of water, but nevertheless, it has some identity of its own. It can kind of travel along and not change and so on. And that's the kind of way that we imagine that things like particles work. There's actually a great duality between the way that black holes work and the way that particles work in this kind of setup. They're both sort of just made of space. So, okay, so we imagine that we have something which has all these different atoms of space. We imagine that perhaps our universe has 10 to the 400 atoms of space right now. It's only a very rough estimate. But then we ask, what's the sort of large scale behavior of all those atoms of space? It's the same kind of question as asking, given all those molecules in water that are bouncing around, what's the large-scale behavior? In the case of water, the large-scale behavior is the equations of fluid mechanics. Well, the big surprise here, which I actually knew in the 1990s, is that when you're looking at these networks and you're thinking about kind of these networks as changing through sort of local updates of every time you see a piece of network that looks like this, transform it into one that looks like that. The network is continually changing by all of these local updates. If you do that and you look on a large scale and you ask, what are the overall equations that govern the structure of this network? It turns out the answer, subject to a bunch of conditions, but the typical answer is it's Einstein's equations, the equations that govern the structure of space-time. And so what happens is, just like you're deriving from molecular dynamics, you can derive the fluid equations with all sorts of footnotes and so on about how that works. And it's been a very difficult thing, which is still not mathematically pinned down. And the same is true of our derivation of general relativity. There's lots of mathematical pinning down, which people have been trying to do for the fluid equations for the last 150 years. So it's not an easy thing, but one can see basically how it works. What ends up happening is that the sort of the large scale behavior of these networks, when you look at them, they behave, they have the same kind of curvature in space and propagation of curvature in space and all those kinds of things as the Einstein equations, and specifically you can derive the particular mathematics of the Einstein equations. I'll mention a few other things. One of the features of these networks is that their dimension is not determined a priori. So the dimension of the fact that we live in sort of 3 dimensions of space, that's something that has to emerge from the model. It's not something that's built in. In fact, we imagine that probably in the very early universe, the universe was effectively infinite dimensional, and it gradually kind of cooled down to be what is now pretty accurately 3-dimensional. We expect that there will be dimension fluctuations that are left over, and that's a potential thing to actually look for in cosmological experiments. We can't yet derive the fact that the universe as we perceive it is 3-dimensional. All we can say is that if it is finite dimensional, it has certain properties, including the Einstein's equations and so on. So let me give you another sort of a little bit more of an indication of how this works. So for example, you can say that the structure of space is determined by the structure of this network. You can ask about something like energy. Energy turns out to be, and I was really amazed that it works out as simply as this, energy is essentially the density of activity in the network. When there are all these updates going on, the more updates that there are going on, that corresponds to higher energy at a particular place in the universe. And so then you can ask a question like, well, how does gravity work? Well, the way that things move through this network is on shortest paths. And you can work out the shortest path in a graph by just saying, if you want to go from here to here to here on a graph, what set of edges do you follow to get there in the shortest way? Well, it turns out that in the presence of activity in the graph, those shortest paths are deflected. So in other words, the presence of energy deflects shortest paths. It changes, in effect, the curvature of space to change these shortest paths. And it turns out to do so exactly in the way that we observe about the way that gravity seems to do it in our universe. So in a sense, the existence of gravity is a consequence, and this is necessarily the case from the fact that one can derive the Einstein equations from this system. The presence of gravity is just this relationship between activity in the network and the deflection of shortest paths. So that's sort of the first thing, is the derivation of kind of the structure of space-time. Another big feature of physics as we know it is quantum mechanics. And kind of the key idea of quantum mechanics is, well, in classical mechanics, we expect that definite things happen. You know, you throw a ball, it goes in a definite trajectory. In quantum mechanics, kind of the big idea is it doesn't go in a definite trajectory, it follows many possible trajectories. And what we observe is some kind of aggregate, some perhaps probabilistic aggregate of many of those trajectories. Well, it turns out that quantum mechanics is something that you don't sort of just add to the system that we're looking at. It is an inevitable feature. It took me 20 years to realize this, but it's an inevitable feature of the kinds of systems that we're talking about. And the reason for that is I've talked about these kind of updates that are going on, and the point is that these updates can be done in many different places in the network. There are many choices of where the updates can be done. Each different sequence of choices defines, in a sense, a different thread of history. And you can make what we call a multi-way graph, where you just trace out all those possible threads of history, all those possible things that could happen in the system. Kind of an analogy is, imagine you're playing a game like tic-tac-toe or chess or something. You start from a particular configuration of the board. There are many possible things that can happen depending on how you move the pieces on the next step. And what we're doing is we're tracing all those possibilities. And sometimes there's a branch where you have one state and there are 2 possibilities for the next step. And sometimes there's a merge where there are 2 states and they merge into a single state on the next step. That process of branching and merging forms this multi-way graph. And this multi-way graph is kind of a map of the possible histories for the universe. So what happens is when you take a slice across this multi-way graph, you say going down the page, it's as if you're progressing through time, you're doing computations, that's the passage of time. But at a particular time, you can just slice across this multi-way graph, and you can ask, of all these loose ends that are left over, how are they related to each other? And you can kind of imagine that there's a space that describes how they're related to each other. We call it branchial space. And essentially, you're just looking at, for any given states here, which ones have common ancestors on the step before, for example. That allows you to say which states are close to which other ones. It gives you a map of this a set of states. So we interpret this map as a map of quantum entanglements. These different states of the universe are different possible quantum states, and this relates to how those states are entangled, how those states are related to each other. And so the basic thing that happens is that this branchial space is kind of there's physical space, which is the kind of layout of this hypergraph. There's branchial space, which is what you get by slicing across this multi-way graph. Branchial space is kind of the story of quantum mechanics. And well, okay, there's much to say about this, but one of the things that's of interest in quantum mechanics is how do we humans perceive the world, and how do we, so, okay, first thing to say is in physical space, it's very important that we are very big compared to the atoms of space. That is why we believe that there is a continuous space that exists in our universe, is because we're big compared to the individual discrete atoms of space. Just like we believe in continuous fluids like water, because we're big compared to the individual molecules of water. And so the question is, what's the analog of that in branchial space? And it turns out that the way we should think about it is, we have this universe which is continually branching and merging these different threads of history, but our brains, our minds are also continually branching and merging. So in a sense, the story of quantum mechanics becomes a story of how does a branching brain perceive a branching universe. And it turns out that the big idea is as soon as we have the concept that consistent things happen in the universe, that drives a lot of what happens in branchial space and so on. There's a very beautiful fact that this phenomenon of gravity in physical space, the deflection of GD6, the deflection of shortest paths by the presence of energy momentum, that idea also works in branchial space. There is a deflection of shortest paths in branchial space through the presence of energy momentum. And it turns out that appears to be exactly the path integral of quantum mechanics. So when people ask, how do you sort of unify general relativity and quantum mechanics, the answer is they're actually the same theory. They're both about the deflection of GD6 by the presence of energy momentum, but one of them is operating in physical space and the other is operating in branchial space. So, okay, so that's a very abbreviated story of kind of a little bit about how we think physics works at kind of the lowest level. Let's go even deeper down the rabbit hole in the few minutes that remain here. And let me tell you about this thing called the ruliad, which is kind of the ultimate kind of abstract object. So so one of the questions might be, okay, so we've got this kind of idea for how we make kind of a machine code for the universe, but let's say we can hold in our hands the particular rule for our universe. Then it's kind of a remarkable thing, because we'd say, why did we get that rule and not another rule? If it's a simple rule, why were we the lucky universe that got that simple rule? Why didn't we get some much more complicated rule? So I found that very mysterious until I realized that actually there's a way of thinking about this, which is what if the universe follows all possible rules? What if instead of just taking a particular rule and applying it in all possible places, you apply all possible rules? How could that generate anything interesting? Well, it turns out that because of this phenomenon of branching and merging, you have all these different possible rules, and different rules can lead to the same states. So that ends up giving one a very rich structure. One can think about it in lots of different ways. Well, let's see if I can find a picture, probably I can't immediately, of what this looks like for Turing machines in pure kind of computation. You can look at sort of all possible Turing machines. Let me see if I can pull that up. Oh, here we go. Might have a nice picture. Okay. Yeah, so this is, let's say, a typical Turing machine. There's a typical Turing machine doing its thing with its head going back and forth. This is a multi-way Turing machine where there are many different possible paths of history. You can ask what happens when you allow all possible Turing machines with all possible rules. What kind of structure does that generate? And then you generate, well, here's an example of the kind of structure you generate. This is actually showing deterministic versus all Turing machines, kind of related to the P versus NP problem. But the basic thing is that you get this whole structure that represents sort of all possible Turing machines, the entangled limit of all possible computations as represented by Turing machines. And so what you realize is that in the end, that sort of underneath this particular set of rules that you might pick for the universe is this ruliad that is the object that you get from following all possible computational rules. It's the ruliad is the entangled limit of following all possible computational rules. So that object, you say, well, that's a very big object. It's also a very unique object. There's only one of it. Once you formally define the idea of computation, you immediately get the ruliad. There's no choice about the ruliad. And so then the question is, well, okay, if that's the case, what is our perception? How do we perceive the universe as the universe is? Well, this is a slightly complicated thing because we are entities embedded within this ruliad. And so we have to ask the question, how does an entity embedded within the ruliad perceive the ruliad? And so here's the thing. If we make certain assumptions about that entity, then there are certain inevitable consequences about the way that the ruliad is perceived. So there actually are two assumptions that seem to be very important. One is that we are computationally bounded observers of the ruliad. That is, we, in our minds, can only deal with a certain limited amount of computation. We can't sort of untangle everything that's happening in the ruliad. We can only see a sort of coarse-grained version of it. It's just like if we're looking at molecular dynamics of a fluid, we can't untangle what all the detailed molecular motions are. We just see this aggregate density of a fluid or something. So that's first assumption. First feature of observers like us is we're computationally bounded. The second assumption is that we are persistent in time. Now that's a non-trivial assumption because at every moment we get made from different atoms of space, yet we perceive that we are persistent in time. We have this belief that we have a thread of experience that persists through time, even though underneath we're made of different things at every moment in time. So with those two assumptions, persistence in time and computational boundedness, it turns out that any slice of the ruliad that is perceived by an observer with those characteristics will have certain features. In particular, it will show essentially general relativity and quantum mechanics. Now, in a sense, this is not quite as surprising as it might be, because we know that if you start from molecular dynamics, you start from a bunch of molecules bouncing around, it doesn't really matter in detail what those molecules are like. They could be like air, they could be like water. They will still generate, they still produce on a large scale. For observers like us, they will generate the fluid equations. So it's the same kind of thing that's happening in the ruliad. For observers like us, one generates the features of physics. Now, there are other questions you could ask about the way the universe works, which are more detailed and which will depend on more on exactly where in the ruliad one is, so to speak. So in a sense, what we think about is we, with our kind of minds and so on, exist at some place in the ruliad. We are looking at the ruliad from some point of view. Another mind will be looking at the ruliad from another place in rulial space, as we call it. Just like one can be separated in physical space and have different perspectives on the universe because one's at different places in physical space, so one can have different perspectives in rulial space. And essentially every mind is at a different place in rulial space. And we can, minds like our human minds are not too far apart in rulial space. It's not too difficult to communicate from one mind to another. If we go further, if we imagine kind of the alien mind, so to speak, it becomes increasingly difficult to communicate across rulial space. And by the way, all these characteristics, like things like speed of light and so on, speed of light is a limitation on how far you can go in a certain time in physical space. There's a maximum entanglement speed, which is the corresponding thing for branchial space. And there's a maximum rulial speed in rulial space, which actually is closely related to the ultimate processing power of the universe. Well, in any case, so one of the things that happens from the ruliad is it's this ultimate kind of representation of kind of what is possible from computation. It's the entangled limit of all possible computations. And among other things, it means that this isn't just something that is underneath physics. It's also underneath other kinds of things. So, for example, one thing it's underneath is mathematics. And just like you can talk about physics in terms of this kind of this structure, we can also think about mathematics. We can think about when we derive a theorem from axioms, we're essentially building up a graph that's just one of these multi-way graphs. And you can essentially build up the structure of mathematics with instead of things representing atoms of space, they represent mathematical propositions. Actually, you can go even lower level than mathematical propositions down to what we call eames, sort of true atoms of existence that are the same atoms of existence. It's kind of the same data structure that makes the physical universe as makes mathematics. And you can go and make that much more explicit. It's actually easier to do experiments in mathematics than it is in physics. And so you can do empirical metamathematics, and you can look at, what is the actual structure of, I don't know, some field. Let's see, I probably have some pictures here. Well, that's, for example, that's Euclid's elements, the empirical metamathematics structure of Euclid's elements. But we can go and look at different, that's the derivation of the Pythagorean theorem in sort of almost ultimately low-level metamathematics. It takes a huge number of steps, but we can also look at kind of the structure of mathematics. Let's see if I've got a picture here. Yeah, there we go. So we can kind of look at metamathematical space, and we can see different fields of mathematics showing up in different places in metamathematical space here. Oh, come now. Not what I wanted. There we go. Anyway, so I was just showing there. Let's see. I was just trying to show you kind of a little bit of metamathematical space, and so how do we think about this? Okay, there's distribution of some famous theorems in metamathematical space. So how do we think about this? Well, what we realize is that we are observers of the physical universe with certain characteristics. We have this computational boundedness. We have this persistence, belief in persistence in time. We are a certain kind of observer of the ruliad that gives us the laws of physics. Well, as mathematicians, we are also observers of the ruliad, but we are different kinds of observers from the kind of observer that we are to make physics. And so there's this notion of the kind of the mathematical observer. They're both like the physical observer. We're dealing with humans being the mathematical observers. And so they have certain characteristics in common, and that kind of drives the structure of mathematics. So for example, here's an example of an interesting fact. So you can think about mathematics in terms of very low-level axioms. You could think about the Pythagorean theorem. You could think about proving it by, first of all, setting up, low-level axioms for the structure of real numbers and doing this and that and the other, and kind of building up to the Pythagorean theorem. I showed that picture of kind of all the steps that it takes, this vast number of steps that it takes to build up from that. So in a sense, you could sort of build everything up from kind of the atoms of mathematics. But one of the things that is interesting is that we humans succeed in doing mathematics at a higher level. It's kind of like in fluid dynamics. We can think about the motion of fluids in terms of these kind of large-scale motions. We don't have to go down to the level of molecules to think about how fluids work. And so it turns out we know kind of experientially that in mathematics we can reason in mathematics at a higher level without always dropping down to the lowest level axioms. But it's not obvious that that will be possible. It's not obvious that you could consistently work just with the Pythagorean theorem and not have to always keep on saying, oh, but how is that derived from the low level axioms of real numbers or something? But you can actually operate at this higher level, just like you can do a lot of things just thinking about fluid mechanics without thinking about molecular dynamics. And so that feature it's the same kind of thing as the fact that we can think about continuum space, even though ultimately space is made from this giant network of atoms of space. In our experience of space, we can talk about it and think about it in terms of this kind of continuum limit of space. And
Stephen?
It's for the same reason, sorry, I'm almost finished. For the same reason that the kind of the point is that the fact that higher level mathematics is possible happens for the same reason as the fact that we perceive space to be a continuous kind of thing. All right, there's much more to say about this, but I will stop there, and I'm happy to take any questions or comments or discussion.
Thank you very much.
My question is, I'm a scientist more than a mathematician, and so I'd like some tests or predictions of what Stephen has discussed.
Sure. Okay. So there are ultimately boatloads of predictions. There is one parameter in our models, which is essentially the magnitude of the elementary time, or alternatively the maximum entanglement speed, or alternatively a lot of other things that are closely related to that. We don't know the value of that. So we don't know at what stage certain kinds of things will happen. But there are many kinds of, sort of strange effects that one can look for. For example, the thing I mentioned about dimension fluctuations in the early universe. The maximum entanglement speed is something that is possibly observable in quantum many-body systems. We don't know the magnitude of the maximum entanglement speed, so we don't know exactly where that phenomenon will occur. We would love to have a prediction like Einstein had for the deflection of light around the sun, where very conveniently everything canceled out and it was just a factor of 2 different from Newtonian theory. As a matter of fact, there turns out to be a possible prediction for photons in orbit around black holes, where the way that our branchial space and physical space work, there may also be a similar kind of numerical factor type thing that can be worked out. One of the challenges with predictions is that there's a great depth, there's a great distance between kind of the underlying theory and what is, what you get to turn a telescope or a particle accelerator to look at. And it's kind of like, the cautionary tale is to look at Newton's Principia, and he computes the motion of the moon and he gets the wrong answer by a factor of 2. And you could have said, oh, well, then the theory must be wrong. Turns out that computation of the 3-body problem is pretty hard, and it took another 150 years to get that answer right. So there's a certain depth of computation that you need to do, and science you need to do to go from sort of the underlying theory to specific predictions where you say, go look for this. But one of the things that's nice is that there are these just totally bizarre kinds of things that you never would have expected to be there, like dimension fluctuations, for example, which you can look for. Now, another thing to say is when it comes to kind of validating the theory, it's a very interesting form of validation, which is already happening, which is that you can use our model of space-time as a practical way to do numerical general relativity. So normally when you study the merger of 2 black holes or something, you would take the Einstein equations, which are partial differential equations, and you'd probably use our product Mathematica to do a bunch of algebraic manipulation and a bunch of sort of numerical preparation. Then you basically go and you discretize those equations and you solve them as discrete equations on a computer. That's the kind of standard way to do things. You go from the continuum down to something discrete that you can deal with on a computer. In our setup, you have something discrete from the beginning and you go up from that, and you have a sort of large version of that limits to the continuum. That is the thing that we approximately at least observe. And so we have started to do computations even on things like black hole mergers, and it's really very encouraging because the kinds of results one gets are extremely consistent with, close to, the kinds of results one gets by going the other way. So it's as if one can, and in fact, the things we're doing seem like people are catching on to them as a sort of practical way to do numerical relativity. So even if you don't care about the underlying theory, even if you don't sort of care about the ontology of the universe, we have a really good way to do computations in general relativity. So that's on one side. On the side of quantum mechanics, same kind of thing is happening. For quantum mechanics, we can compile quantum circuits into our multi-way graphs. In fact, a chap at our company just won a competition a week or 2 ago now for optimizing quantum circuits. And that was done by taking a quantum circuit, a standard communal garden quantum circuit, compiling it into multi-way systems, using a bunch of technology there that comes from the way that multi-way systems work, and then going back to quantum circuits again. So it's, again, a case where we can kind of validate our model by just showing that we have a way to deal with things which are exposed as sort of standard quantum circuits, but then analyzed in terms of our model. For quantum field theory, we don't yet know how to do that. We strongly suspect that we will have a way to do actual computations in quantum field theory more directly and more efficiently than has ever been possible before, but there's a lot of technical difficulty in actually doing that. That will be another kind of path. The thing we'd really like to be able to do is to make sort of a gravitational microscope that can kind of see down to the individual sort of the discrete structure of space-time, for example. There is some hope that that's possible in a black holes when they have critical angular momentum. It's possible that what happens there is that there is essentially the black hole, there's a piece of the universe that would kind of disconnect, which is something can't happen in general relativity, but it can happen in our models. And right at the sort of point where the disconnection can occur, there are a very small number of basically graph edges that hold it together. And the result of that will probably be kind of a shot noise in gravitational waves. Again, we don't know the magnitude of it, and it's not an easy thing to measure, but it's something where one should be able to see that eventually. And what I'm expecting is that there's probably some very clever experiment that somebody can invent with gravitational lensing or some such other thing, where in fact we'll be able to build a gravitational microscope. We just haven't figured out how to do it. It's kind of like the long-term story of technology, which is, you take what the universe offers you and you figure out how to sort of turn it into something that's useful for human purposes. Here, what we're saying is we've got the universe, we kind of have an idea for how it works. Now the question is, how do we connect what's happening down at the sort of microscopic level of the universe to things that we humans can sort of care about? And there's a whole, I'm not going to talk about this here, but a whole big story of what we're calling observer theory is the story of kind of what kinds of things do we humans care about? And that's important in determining how the theory works. But that's also a branch of that is also important in understanding what kinds of things are, quotes, predictions that are going to be things that connect to sort of our everyday experience of things and that we can actually sort of extract from kind of the underlying structure of the theory.
Thank you very much, Stephen. I hope that answers your question, Charlie. Yes. All right.
Can I ask one more question, or there's no time?
Yeah, there is actually no time. So unfortunately,
looks like we have 3 minutes. I'm here for another 3 minutes. So
you're here for 3 minutes.
Okay,
okay, so let's allow the operators to prepare a little bit for the next set, and the volunteers to keep the other public talk attendees outside a little bit longer, and then please pose your question briefly, and then
be quick.
Yes.
So first of all, congratulations for all the work to you and your team. And my question is about the quantum mechanics part, because you mentioned that indeed you can see the features of quantum mechanics. I was wondering, do you see also kind of emergence of non-local effects then in your model?
Yes. Yeah, I mean, what basically happens is there's branchial space and there's physical space. And effects in quantum mechanics are kind of a story of interactions across branchial space. And the connection between branchial space and physical space, only in specific cases are those two connected. So for example, when you look at, I mean, the story of, probably the story of these holographic principles, ADS-CFT correspondence and so on, that is probably what one is seeing there is a correspondence between branchial space and physical space. Those two, again, it's a sort of a slightly longer story. There's this thing we call the multi-way causal graph, which is a kind of combined object which combines those two. And physical space is one projection, branchial space is another projection. But essentially the non-locality of quantum mechanics is a consequence of the fact that things can be related in branchial space while separated in physical space. And I mean, there's more to it, but that's the basic idea. And the thing to understand, in branchial space, what we think is the case, although the mathematics of this has been rather difficult to deal with, we think that basically position in branchial space is essentially quantum phase. That as you move around in branchial space, you can think about that as changing the phase of a quantum state. And that's why, for example, when you have, I talked about deflections in branchial space and the path integral. If you know how the physics of this works, the path integral tells you that there's an e to the I times the action that is the weighting of a path, and that the fact that the presence of action, energy momentum, basically causes the phase to change. That's a result of the idea that position in branch Hill space is related to quantum phase. Much more to say about this, but there's much written about this, and you can find, if you look at wolframphysics.org, I think that's probably a good starting point for understanding this